All right, welcome everyone to my CppCon talk, Fast and Small C++. Looking at the large screen here, I should have titled it Huge C++ or something like that. I'm Andreas Fertig. I'm a trainer for C++. I offer services worldwide, remote or on-site. If you're interested, just contact me. I'm also the author of a tool called C++ Insights. In case you haven't heard of that, you will see it during this talk at least once. I'm German. Some folks of you might be able to tell by my last name. My last name is a very common German word. It's an adjective in German. It translates to English as finished, ready, complete, or completed. So in summary, I would say a positive, nice name, right? Usually use it in a positive sentence. You can also use it with a slightly different meaning, like I am tired, I'm exhausted, which would be the meaning today because my body still fights with the jet lag, and so I'm feeling a little fertig at this point. And since I'm doing talks, I'm looking more into my last name and I'm collecting stories. And what I noticed about that is that we recently had the Olympic Summer Games in Paris, right? That wasn't a big realization I had. What I realized is whenever they start a race, they shout this three-part sequence, ready, steady, go. Whenever they start a race, they started by yelling my last name. Ready, it's a translation, right? Beautiful. Now you know what ready translates to in German? Fertig, right? So are you ready to do it in German? Ready, steady, go. It translates to auf die Plätze, fertig, los. So what I realized is we Germans, we require 3 words to kick off a 3-part sequence. So you have to listen very careful to not run too fast or swim too early. And my last name goes second. Languages are fun, right? The spoken ones and the programming languages. So let's get into an easier topic, C++. This is what you're here for, right? And not a German lesson. Let me start by telling you I have good and bad news for you. I'm not a standard library developer. This is the good and the bad news, by the way. It's the bad news because it means I will present 2 things or so from the standard library, and since I haven't implemented or created them myself, I might not be able to answer questions like, why is it that way? I can only show you how it works. But it's also a good thing, because that I'm not a standard library developer means that I present you readable code. I mean, code that a large amount of us considers readable, so it doesn't start with double underscores and uglified names. It's the beautifulness if you can just use the standard library, and if you're not a standard library developer as a presenter, right, you can do that. So what I have here is titled compressed pair, and what you're looking at is a construct you're potentially very familiar with. It's a unique pointer. The most common use case for a unique pointer is you provide one type, the type of the pointer that this unique pointer should wrap and should maintain, such that we have a memory-safe construct at this point. Another use case, in my experience, a little less frequent used, is to provide a custom deleter, to perform a special action during construction and not just delete. This enables us to use a unique pointer together with something where we never really set new for. My example here is having a fopen returned its file object. I store that in a unique pointer, and I say, when you destroy it, please call fclose instead of delete. So with that, whenever I leave scope, my unique pointer here manages my file handle and closes the file. Perfect. I'm safe. This is what I like. Very good. Now, I'm doing this talk because I enjoy writing software for the embedded domain. I did it for a long time, and I wanted to be either fast or small or sometimes both at the same time. Means I have little resources, a few kilobytes of RAM or ROM, and I don't waste or I don't want to waste any of that. Looking at the code you're seeing here, what we all want, I assume, is that this unique pointer has the size of a pointer, right? It should store a pointer. We don't want to pay more for it. Truth is, the way I'm doing this here, it has the size of 2 pointers because it must store a pointer to this deleter function that I provide at the fclose, which might be reasonable, but I consider it sad because the address of fclose is known at compile time and at link time, so why do I want to pay for it with an extra pointer, which also costs a little time to access? I don't want that, personally, at least. So what can it do, or what does the standard library do to help us out here? There is an optimization technique that has nothing to do particular with the standard library. It's called the empty base class optimization, EBO. And that says if you have a class that's empty, so it contains no non-static data members, it would have the size of 0. But the moment we are starting to ask for the size of this thing with size of, it says 1, because it must be addressable in C and C++. That's the rule. What EBO now says, if we have such an empty base class and we derive from that, the empty base class does not contribute to the size of the derived class. In my example here, I have this empty base class base. It doesn't have any non-static data members, just the function fun. I derive from it in derived. Derived comes with an int 32t. I gave you a specific type here. And if I do the size of dance now, we can see the size of derived is equivalent to the size of an int 32t. So this is what EBO does. The nice thing is, as usual, I can still access member functions from the base class. So on my derived object that I created, I can call the member function fun from the base class. And this is the base trick that we want. We want to be able to derive from something, don't pay for anything, but be able to invoke a function. We do this, or the standard library does that for us, all the time when we use a unique pointer with just one type, because it comes with a so-called default deleter. This default deleter happens to be an empty class. The only thing it carries is a call or parent operator, depending on how we want to call it. And that thing calls delete on the pointer. So it's a very fancy way to say delete. Yet it gives us the abstraction we want, because that thing is empty. And now here's a stripped down implementation of unique pointer. Unique pointer, no news here, is a class template, comes with a class T, it is the type we normally provide, but also a second template parameter, which is defaulted to the default delete class that I just shown you, typed with my type T. Now internally, instead of storing a plain pointer of T and the potential pointer to the deleter, what the unique pointer does, it stores something called a compressed pair, which is typed with the type of the deleter and a T star, the type I provided. The rest then is we have the option simplified to construct the unique pointer with a single argument, presumably the storage that we want to hand to the unique pointer, hopefully previously allocated mid-make unique. We have the option to pass 2 arguments to the constructor, the pointer and the pointer to the deleter, like we saw it with fclose. And in the first case, mpair is simply constructed passing the pointer to it. In the second case, we are passing the deleter and the pointer to it. The rest, you know the dance, a unique pointer is not copyable, so I deleted the copy operation. I implemented the move operations. And the magic now happens in the destructor. In the destructor, we are reaching for mpair's second type. And if that's non-null, this is our pointer, then we are calling mpair.first with mpair.second. So this is our pointer. The implementation of compressed pair could then look like this. This is using C++20. You're saying compressed pair is a class template, takes two template parameters, t and u. I make two data members out of that in my class, first and second, and I flag both of them with C++20's no unique address. With no unique address, it means neither first nor second might occupy storage space if their classes or types are empty. So this is the better trick that you can do if you have C++20 on your hands. When I started looking into this and preparing this talk, at least Clang's libc++ implementation had a more complicated implementation where they really had two different class templates and they figured out whether the base class was empty or not. And I checked it this morning, and this morning was around 7 o'clock or so. And the GitHub said that 19 hours ago at this point, so maybe now 24, they changed their implementation. Basically, if they are in C++20 mode, they're doing exactly this. Okay? So this is the easiest way you can do it. And the gist of that is we are trying to leverage the fact that if we have an empty base class and can just invoke a call operator on that, we don't have to store any pointer to the function we are invoking. So modifying my original example, this is a handy way I like to do it in C++20. I can say I have a using alias being a template, takes a type name t and a C++17 auto non-type template parameter, call that one delete fn. I'm creating this using alias unique pointer deleter. That one points to a unique pointer of type t. And now it uses another C++20 element. It uses a decal type on a lambda. So in C++20, we can use captureless lambdas in unevaluated contexts. And decal type is such in context. So I say here, my second parameter to a regular unique pointer is the decal type of a lambda that's captureless. It only takes a t star as argument, and internally it invokes this function I passed in as the second parameter, delete fn, on the object I passed in, or the pointer of the object I passed in. With that, you can for now on say that you're creating a unique pointer deleter of type file and provide the function fclose to it, and you simply say fopen. You no longer have to say a second parameter. Beautifulness here is my unique pointer now shrinks to the size of a single pointer. This is what I want. But I still can call a function that's available, like fclose, without having to pay extra for it. Nice, right? Can we do better? Okay, you're still digesting your lunch, I understand that. Do you want to do it better? So the answer is, yes, we can do it better if we are using C++23. Because in C++23, we can have a static call operator or a static array index operator, which is not relevant for this piece of code. And that means I can have a lambda whose call operator is static. And I say that by putting the keyword static into the lambda. And that means, as for every member function that's static, it doesn't come with the implicit dispointer, or as it's referred to in C++20, the implicit object parameter. With that, you save at least one assembly instruction. It might go up to 3. It's not huge, but it goes down a little. Okay. So far about unique pointer. Let's talk about another kind that's in the standard library, small string, or string in general. If you would have to implement a string, I think it would be very reasonable to quickly come up with something like, okay, our string needs to have a data member that tells how many characters are in the string currently. Since we are allocating from the heap, we need to store the information somewhere Do we have more capacity? So what's the actual capacity? Size can never be larger than capacity, but maybe equal. And then we need a pointer to the data, and we're good. Yet going to the heap for just one character, for two, for three, for a small amount of characters could be slow. So we don't want to pay for that. So this is why the small string optimization was invented, saying, okay, if we have a certain number of characters, we call that a small amount of characters, we don't go to the heap, because our string implementation brings a small array of characters piggyback inside it with as a data member. In my code here, this is MSSO buffer, size 16, so I have 16 characters here that I can store before I have to go to the heap. It's actually 15, because I need to subtract 1 for the null pointer. And because I now have two states, I can be in small or in long string mode, I need a Boolean to indicate in which mode I am. And assuming we are talking about a 64-bit architecture, this struct here sums up to 48 bytes. If we are referring to C++ inside, and we enable the show padding information transformation, then we can get a confirmation here. Size is 48 bytes. The alignment of the struct in general is 8. I have the 3 data members in here, size, capacity, and my mdata pointer. They are all 8 byte in width. And then I have my SSO buffer here. You can see it's also zeroed out because I used uniform initialization. And then I have the bool here, size of 1, everything is good. And then I see that. 7 bytes of padding. They're required because I can build an array of strings here, and then the second element in this array must be aligned as well, and it is only aligned at an 8-byte address. So this is why I require the padding bytes. These padding bytes are terrible. They're hurting your performance, because your cache line size usually is something around 64 bytes. I just wasted 7 for absolutely nothing. There are times when rearranging data members helps. In this specific case, I cannot rearrange it in any way that I can get rid of the padding bytes here. Maybe that's okay, because I would say 48 bytes is too much anyways for that string implementation, right? Now, as an exercise, just in your brains, and the people on YouTube watching that later, they have the opportunity to pause the video at this point. I don't have that much time for you. The question is, if it was you who had to implement such a small string optimization, how would you do it if the one limitation was to not exceed 24 bytes in total for the size of string? Because this is what the rest of my slides are based on. This is not in what the standard library does in reality. They have a little bit more flexibility, but to make them comparable, I limited everything to 24 bytes. So think about, how would you do that? And the more specific question is, for what scenario would you want to optimize? Because that's always the key. Now let's see. Now my browser is gone. Nice. Come on. Here we are. All right, that gave you a bit of time to think about that. It was intentional, of course. So, first implementation I like to present is Libstdc++'s implementation. That's a standard library that ships with GCC, at least by default. What they are doing there is they say we have this struct string, and we started with a pointer to the data, ptr. Next member is a size t for the size of the string. And then they start playing tricks. Then they have a union in there, because they realize the fact we don't need the capacity in the small string buffer at the same time necessarily. If I'm in small string mode, I know the capacity I have. It's the size of the buffer I reserved for that. It doesn't change, it's fixed. Only if I'm going to long string mode, I need information about how much dynamic memory did I just allocate, or do I have in general. So they have a union here which overlays capacity and the small string buffer. That means that their small string capacity is 8 characters. -1 for the null terminator makes it 7 characters that we can store in a small string here. Remember, the original implementation of GCC is capable to store more. It's because I limited everything to 24 bytes in total. Then we will see a couple of member functions, static member functions that come up all the time. We have one that's called capacity here. It simply gives you an indication what is the maximum size of a string I can store for this string type here, and that's whatever the size of your size t is. SSO capacity, as I said, is the size of mbuf -1, so 7 in this case because we have to store the null terminator. Then we have a function that simply checks whether the things fit into the small string buffer by checking whether the length of a provided string is smaller than the SSO capacity. And then we have the magic function isLong. That one checks whether we are in long string mode or small string mode. And it does so by comparing mpointer to mbuf. If they are not equal, it means we're in long string mode. Otherwise, we are in small string mode. Because if you look further down, in the default constructor, everything is initialized to small string mode. Mpointer is initialized with mbuf. In the case where I have a constructor that takes a pointer and a size, we first check when initializing mpointer, does the string fit into SSO? If so, then initialize it with mbuf as before. Otherwise, allocate dynamic memory up to the size we require, update the size, initialize to be kind to the C++ type system, the union with mbuf, and then in the constructor's body, if it's long string mode, update the capacity, make that the active member. And because it's an incomplete implementation, next, of course, we would copy the data. Otherwise, that exercise would be pointless. Then I have the 3 potentially most important member functions of a string in here: size, data, and capacity. Size and data are super simple in this implementation. For size, I can directly go to the size member function. For mpointer, for data, I go to mpointer. Quick and easy. For capacity, I get a branch. I have to check. Is it long mode that's active? Then return capacity. Otherwise, SSO capacity. So, as I said, I don't know what the original motivation was, but looking at the code, we can say, well, this implementation seems to optimize for access to size and data. Potentially, these are very frequently used operations, because if I create a string, I will read it. And I will read it maybe multiple times. That requires accessing data. Maybe even size all the time, because I don't want to go through the null pointer. I want to know upfront how large the string is. Capacity is required if I'm appending to a string. That might be less usual. I don't know. For your system, it could be different. But the code here looks like the optimization goal was going for size and data speed. Can we do it differently? Of course we can. We have 3 different standard libraries that are common, right? So this is Microsoft's implementation from the Microsoft standard library. They start with a union. They say we have the pointer and the small string buffer overlaying each other because we don't need both at the same time. And then they have the 2 members of size t, msize and mcapacity. They're doing the trick a little different. Max capacity for that version is also the one of the size t. SSO capacity is as before 8 bytes in this implementation, so what you can store is still 7. Fits SSO is as before, and is long now does a different check. Of course, it has to. It checks whether the capacity exceeds the small string buffer's capacity, because this is how that implementation knows that it's in long string mode. Same thing we are talking about, right? But different approaches. Now, default constructor is the same. Small string mode is the default. The constructor with 2 arguments here. It initializes mbuffer. We have to make one member of the union the active one first. Then we set size. Then we set a capacity. And there we figure out, are we in small string or in long string mode by checking does the string fit into the small string buffer. And then we set that one accordingly. And then in the constructor's body, as before, we are checking, are we in long string mode? If so, we are allocating data from the heap, and then we would copy the data. This changes the 3 member functions, size, data, and capacity now. They also can fetch size directly by accessing the data member msize. Data now requires to branch. They have to check whether they are in long string mode, then they return mpointer, or in small string mode, they return a pointer to mbuff. This is how they are doing it. And capacity now is the fast path, no branch here. So maybe a different optimization in mind, different setting for performance. These were the 2 easy ones. Did anyone guess it like that? I mean, you didn't really have time, so it's totally fair. So behold what libc++ does, which comes from Clang, which, by the way, is also the newest from these 3. They're doing it totally different. They start by saying, let's ignore the first line here, that static unsigned thing. They have 2 structs in it. Call them normal and SSO. And did I mention that I like embedded development? They start doing the bit fiddling. Because they now say, in this struct, the very first bit, the most significant bit here, we call that one large, and it's only the size of 1 bit, followed by capacity, which is a size t, but technically also a bit field, which has the number of bits of a size t minus 1, because 1 bit is required for large. So the capacity of my size t here is reduced by 1 bit. And then we have the member size in here, size t, of course, and the pointer data. In SSO mode, they do it a little different. They say we have uint 8 t's now, but it's still the first bit, the most significant bit. We call that one large. Followed by a now only 8-bit with size member reduced by 1. So 7 bits here for storing the size in small string mode, which, as we have seen, seems to be reasonably more than enough bits than we need to store a string like 8 or 16. Then they introduce padding bytes. I said I don't necessarily like them, but they are here to make the 2 structs consistent, because after this padding bytes, we have reached a point where we can say that large plus size plus padding equals the size of a size t. So the first 3 members in this SSO struct together, it's the size of a size t on a 64-bit platform. And now they place in their small string buffer in form of a jar array data, and that one has the size of the normal struct size minus 1 size t. Considering that the normal struct size is 24 bytes and the size t has 8 bytes, we have 16 bytes of small string buffer capacity. Reduce it by 1 for the null terminator, you can store in this implementation 15 bytes of payload before you have to go to dynamic memory. So this seems to be what they optimized for. As large as possible small string buffer. They pack these two in a union, call the members large and small, and you can see it doesn't fit on one slide anymore. So on the next slide, we have the usual candidates, max capacity. This is now the power of 2 of the number of bits of a size t minus 1. So not the same maximum capacity than the two other implementations can take. My SSO capacity, on the other hand, as I said, 15 bytes of payload. That's quite good. Islong now checks in this packed union that I created for the small members large bit. Is that one set or not? Default constructor constructs a small string, and the two-argument constructor here also starts with initializing the small string, and then it checks in the constructor's body, does the length of the string fit into SSO? If so, we are updating the size in SSO mode, and if not, we are flipping the bit in large mode, updating the size, and then we would copy the data. For the three member functions, size, data, and capacity, that means they now all the time have to check in which mode we are. So it's practically guaranteed that in every mode you get a branch. But you have the best SSO capacity. As I said, it depends on what you want to optimize for, what is important for your application. You can do different things. Remember, the goal was to have 24 bytes in total. You've seen 3 implementations so far. Assuming we want to optimize for SSO, maximum SSO capacity, can we do better? Yes, we can. Facebook? No. Okay, nice. Maybe we should have chat later. So, what you're going to see now is something I learned from another CppCon talk from 2016. It's the implementation of the string that Facebook ships. And for YouTube, you can pause now and can go and find Nicholas Omrod's talk from CppCon 2016. It's linked on the next slide. I really enjoy that talk. It's only 30 minutes. It's worth a watch. I will spoil it now a little, so sorry for the audience. Please don't leave. I hope my talk is great as well. So, as you can see, what Facebook does here, it's appearing similar to what we just saw from libc++. They have a struct normal and a struct SSO. They don't do the bit fiddle stuff here. They say normal has a data member that's a pointer of char data, a size t size, and capacity. The comment here says capacity is virtually reduced by 1 byte. Keep that in mind. The SSO capacity or the SSO buffer, the struct they are creating here, is the full size of normal, full 24 bytes. So they don't do the bit fiddling stuff at this point. They pack both of them in a union as we saw it with libc++. Max capacity is the power of 2 of the max capacity of a size t minus 1 byte here. SSO capacity, they now say, is the size of the small string buffer minus 1. Because we have to store the null terminator, right? So that would mean 23 bytes payload in total. Sounds awesomely good. But how do they know how many characters are in the small string buffer? They only have one variable at this point that's called data. So what they do is they have a function called getModeByte. And that mode byte fetches the most significant byte from this SSO data member. It reads that one out, and in its islong mode, it checks whether this most significant byte, the 7th bit, is active. The original implementation of Facebook string knows 3 modes: small string, medium, and long. And the medium string mode is the 8th bit. This is why it's arranged like this. So they're checking whether the 7th bit is active. Now, as the others, they initialize everything in small string buffer mode in the default constructor. If we come to the constructor taking a character and the length, they initialize their small string mode as well by default, and then they check, does it fit into SSO? If so, and this is where the magic happens, they say, give me the most significant byte from the small string array, and in that they store the SSO capacity minus the current length. So instead of storing the number of bytes that this string currently has, they store the number of bytes that's left until we are at the end of our capacity. Now that means that the number they are calculating there, the larger the string is that you're storing in your SSO buffer, the more that number goes down to 0 until it finally reaches 0 when there is no more space left. And the beauty is now 0, incidentally, is also the value of the null terminator. So they combined the number of characters in that string, or the remaining ones, and the null terminator in 1 byte. And this is why they can store 23 bytes of payload in their small string. Brilliant. Other things, Constexpr. I always have a hard time telling people that Constexpr is really great. And this one now is the best I can do. It comes from a consulting project. I was called in. Customer was running out of RAM. They had a small embedded device, a few kilobytes of RAM. And after a little investigation, I found out what the device mainly did was sending around messages, mostly strings, in the network. Some of them were constructed at compile time, others were runtime generated strings. So I stumbled over this class they had in, it's called fbstring. It's more or less similar to what we are about to standardize for C++26. It's a class template that takes a size tn, and this n is used to create an array of jars in this fbstring class. It also carries a size to tell how large this string is. Comes with a default constructor, comes with a constructor taking a constchar star, obtaining the length, copying everything over, as a size member function and a function to convert it to a string view. Now this is what they had dozens of times. And you would use that by saying, okay, I create a fixed string on the stack somewhere, I name the size of that thing, and I put my string in it at compile time. What I found out is, big surprise, we developers are sometimes a little lazy, and counting characters is not really the thing we are totally into. So what a lot of them did was to say, oh yeah, I need that string. Oh yeah, 50 characters, that should be enough, right? Whether it's just 24, 26, who cares? It fits, it compiles. So they over-allocated. They realized that, and they provided this makeString function that's also here on the slide, which does this template trick that derives the size of the array and constructs a fixed string with that. So it was the perfectly trimmed fixed string down. And when I saw this code, I started asking, why don't make it Constexpr? And they told me, no, that wouldn't help. It's already static, it's already const. What would Constexpr do? Long story short, we had a longer argument, and I convinced them to, well, let's try it out, right? How bad can it be? I mean, it's just trying out something. And this here is the code from the slide. Can make it a little larger here. There's the code from the slides. There's one change. You can see the capitalized Constexpr I have in here. This is a macro. The left-hand side compiler defines this macro to nothing, and the other compiler defines this macro to Constexpr. Okay, so this is the idea here. Both run with 0 for the moment. So I have two different compiler runs, one doing the Constexpr dance, the other one did it as it was. Any guesses what's the difference are in 0? So I can tell you in 0.0, the original implementation takes 209 lines of assembly. Let's ignore the fact that there are a couple of blank lines in Compiler Explorer that might not count. My Constexpr version at 0.0, not sure if you guessed that, 78 lines of assembly code. But who goes in with 0.0, right? So let's do something reasonable, go in with 0.3 for both. So 0.3 looks much better in the original version. 42 lines of assembly, this is what we want to see, right? So once again, why the Constexpr dance? Oh yeah, look at that. It's 31 lines of assembly. So still less. Maybe not that significant anymore, but still less. The thing is, the lines of assembly code are not the most important thing here. Let me walk you through. This piece of code here, this is what you don't want. Because what this piece of code does is initializing your static global object at runtime by copying the data that's in the ROM into the RAM. So this piece of code here means that you're allocating the same string that's already present in the ROM again in the RAM, and then you pay with time to copy it over. The difference between the Constexpr and non-Constexpr version in lines of assembly is that on the right-hand side, this piece of code is not present. So it's not only that it's not there, it's also this work has not to be done, and you're not wasting your precious RAM with information that's already there in the ROM. And if you want to see how great that thing is, because I think it's even better, have a look at that. GCC shows it better than, Clang shows it better than GCC, but both doing it equivalently. In this version, the compiler exactly understands the layout of this object fixed string. The first quad here contains the length. This is my size t, followed by the string, by the array. The ASCII I here says it's a string, followed by, because I over-allocated 28 bytes that are zeroed out, followed because it's not optimally aligned by 6 padding bytes. So the compiler here exactly understands my layout of this object. And you can see here my object X. When I use it, I do this down here, I print it out. The compiler knows it can fetch it from the ROM. So this is the power of Constexpr. It's not just about saying, oh, I'm very close, or it might not help. It can really trim things down. So long story short, they fit everything in they wanted at the end of the day. And this is the best I can show you, so far at least, for what Constexpr can mean for your code. Because I'm certain that I do not want to pay for what's on the left-hand compiler. It's just a waste. And this is one of the few cases, usually this, in my experience, this never comes together. But this talk is titled Fast and Small. And usually you have to decide whether you want to be fast or small. This here is a combination of both, and that's very rare. All right, what else do we have? There's a thing called the initializer list, right? You might know that. You use it whenever you're using uniform initialization together with things like, say, you stood vector, stood list, stood map, or your own data type. And aside from simply creating and passing objects to the constructor of these types, I can also create a initializer list somewhere in a function on the stack and invoke another function passing this list to it. I used a simplified version here without classes and constructors, which we would normally do to, well, get rid of any distractions. So I have this few lines of code here. If we once again go to C++ Insights, comes with another transformation, show std_initializer list. So if I do the transformation here, then just in case you aren't aware of that, what your std_initializer list does is, in the background, the compiler always performs this transformation. There is a so-called backing array. And that is that a compiler creates a const array of the std_initializer list's underlying data type with the size equivalent to the members in the std_initializer list, and it copy constructs all the elements you provide to the std_initializer list into this const array. The real std_initializer list then is just a pointer in the length. In most implementations, at least, they store. So whenever we pass that one around, it's a very cheap data type. But it's a non-owning data type. The backing array here is on the stack. It's not within std_initializer list. Okay. So this is what a compiler does. Excellent. Why I'm telling you this, right? Well, let's forget std_initializer list for a moment. Let's say we have a different scenario, code I've never wrote before, honestly. Let's say I have a function receive. That one takes a const int list array of size 4, just a random number. And then I have the function fun as before, and fun creates a const int list of size 4 on the stack, puts a couple of values in it, calls receive as that one. It's a std_initializer list, basically, without being a std_initializer list, right? But it helps us to reason a little easier about that. So if I'm looking at this in Compiler Explorer, we can see, by the way, this one runs with 03 in the first place. The values 3, 4, 5, and 6, they're constants. They are there. They are in the ROM. In fun, when I'm using them, they're mem moves. They're once again moved from the ROM to the RAM. So it's a little like in the example we saw with Constexpr. We are paying for something we might not want to pay for. Space and time. I don't like that. Don't know about you, but I don't like it. What if we change the game? What if we say we make this list here static? Now the function fun consumes 2 lines of assembly, because once again, like in Constexpr example, it can refer to what's already in the ROM. Without a static, I have to pay for copies. And the reason for that, being as it is that even with 03, the only way the compiler could optimize away these mem moves is if it can prove that receive does not recursively call fun. Because there's a guarantee in the standard in place that if you have a recursion, all the block local variables you create in your function have a unique address with each recursion step. So this is what forces the compiler to copy, despite maybe better knowledge, to copy the data from the ROM to a specific region in the stack for this single step. It cannot prove here that there is no recursion going on because I didn't provide implementation for it. So it only sees the forward declaration. It has no chance at this point. It gets better if it can see the implementation, but still it's up to them whether they consider it provable enough to perform this optimization. If we make it static, as we had it here, then it's no problem. The compiler can optimize that away because now it knows it exists only once in this entire function, regardless how often we have a recursive step being here. So this is equivalent to our std initializer list, right? This is why I brought it up in the beginning. So if I modify this example from the beginning, saying, okay, I have the std initializer list as I had it, what does all what I told you now help you? You do not control the backing array. Making the std initializer list, in this case static, would not help you, not in total, and if you're creating a std vector, you are not creating the std initializer list by hand, so you have no chance making that thing static. Now if you look at this example in GCC here, GCC 13.3, by the way, 03 on, we can see, yeah, it translates to what I just showed you. The compiler, of course, understands we have the constants in here. We pay for the mem move. Because it's the exact same scenario. The compiler must encounter the fact that this thing is being called recursively, so it must copy the data and must guarantee us a unique address. Yet in this specific example, the compiler could say, well, I know that all the initializers are known at compile time. And if we just modify the standard a little to allow us more freedom and say, well, maybe we do not need a unique address for the backing array at this point, we would be far better off, right? So all the examples I showed you so far, they require you coding, which I think you enjoy. This one here requires you to flip the switch. If you're flipping to GCC 14.2, you can see the function fun got much shorter. Because in C++26, we made a wording change allowing compilers to make this backing array static in scenarios where all the initializers, for example, are known at compile time. That could change your program a little because now you could see that the std initializer lists pointer is the same all the time in a recursion, but this is what C++26 says. If you're looking close at what I present you here, you can see the words I'm saying might not exactly match what's on the slide because I have C++17 enabled. What we introduced with C++26 was considered a defect report, a DR, which can be retroactively applied to all the previous standards. So if your compiler wants to do that, as GCC does, they can do it for all the previous standards. So this is a change where you require a new compiler, and so far, I think only GCC implemented it, at least Clang didn't, and you do not have to switch the standard. You don't have to move forward to 26. It can simply come in. Sometimes good thing happens with a compiler upgrade, right? Doesn't have to be, but sometimes they do. All right. That's it from my side. I hope you enjoyed it. If you're more interested in the topic, I'm running a post-conference workshop. We still have a couple of seats free, so if you still want to join, you can do that. We have a few minutes left for questions, so before I open the microphones, which we have to the left and the right for you, let me just say, I'm Fertig. Thank you.
First,
Please.
Thank you for a very enlightening talk. Could you show one of this, like either Visual Studio or Clang version?
From the last example?
Yeah, well, one of the two unions.
One of the two unions, so let's see, wait.
Well, I guess there are all three unions, but GCC did it differently. So either Visual Studio or Clang. I have the same question for both of them.
So you're talking about...
Yeah, well, this one is good.
This one is good.
The function get mode byte, or for Visual Studio it would be is long, always reads at the particular version of the union regardless of what's put there. Isn't it technically UB?
You mean because I'm always accessing the small union part, right?
I understand what you're trying to do in bits are bits and all that, But isn't it technically UB to read the version of the union that you didn't put there?
Technically, yes. As far as I understood, are two things. First of all, if you know that your compiler blesses this behavior is okay, it's okay. Since libs,
well, they are the library, but if I were to write something like this, I wouldn't be able to.
It's not only that. I understood that they also encountered issues once string became Constexpr, because then this is UB, and they had to modify it, but I haven't had the time to look into it. So the first version I saw in Constexpr mode, they said we are always going to the heap, and we are not checking the SSO mode. We are knowing we are constantly evaluated, so we are not doing the UB stuff. Okay. But they changed that recently to be able to have a small string at compile time as well. But you're right. It's I haven't figured out.
Would using Bitcast is Constexpr now. Would using Bitcast, which is basically memcopy, would memcopy solve this?
No, I don't think, because you would still have to access the not active member.
But you wouldn't be accessing any member. You would just say memcopy 24 bits out of it and look at as a bit pattern and look at the senior bit.
I see. Yeah, maybe that's what they are doing. Yeah, that could be.
That's exactly what we do.
That's what you do.
Well, something like that, yeah.
Okay. So that just for the record, the comment was that at least one of the participants here does exactly that. So memcopying or using Bitcast to get a value out of the union and then being safe evaluating the bit.
Okay.
Yeah. Thank you. I'm not sure who was first.
Okay, yeah, so thank you for the insights. And as a fellow German, like, the jet lag is also making me fertig.
Nice.
My question is also on the short string optimizations, because you mentioned on the three final functions that we always looked at with size, capacity, and data, that they have like different optimization goals because of the branch that we potentially get, right? So my question is, would we get a branch? Like, they should all be like C moves, like conditional moves, or even branchless programming, like get the flag, do a bit mask, but there shouldn't be like a branch in there if we properly do this. And then it should collapse to like a single assembly instruction, maybe for the ones where we don't need to do anything, and like 2 or 3 ones for the others. So it should be kind of negligible.
It appears to be far from that simple. So, for example, GCC's implementation, I put that up, so Libstdc C++, their check-in is long, where they appear to only compare mPointer to mbuff. That's more costly than Microsoft's version, where they're comparing 2 integers, because here we have with mbuff to access the address of a data member. And the code I saw when I compared it at least did not agree with what you are wishing. Let me say it like that. I understand that it seems that everything should be falling together, but there still seems to be code, and this is where the implementations really differ. And this can come from the age, so Libstdc in general is, I would say, no, MSVCs I think is older, and then comes Libstdc, but they had to rewrite the string implementation. So yeah, they could put in different optimization ideas.
Okay, thank you.
You're welcome.
Hello, thank you for the talk.
Hi.
I think my question is sort of similar to Fedor's question, but it seems like all of the really cool short string optimized strings rely on like, not just the union thing, but actually multiple compiler extensions and not standard C++ behavior. Things like the packed struct, or even things like the bit packing bit field trick, which is not standard compliant because the language does not say that bit fields are in the order you write them in. That those 2 bits could be somewhere else according to the standard, but in practice, most compilers probably put them in the same place. So I guess my question is, can you write one of these in standard C++? Because they seem to rely on lots of non-standard tricks to achieve all of the really cool, fancy tricks.
So as far as I can tell, if I haven't overlooked anything, the versions from Libstdc and Microsoft, they're standard compliant. They are not doing anything. They are using the union. They are accessing the members validly. So they don't do anything I'm aware of that would not be standard compliant.
Right, but they only get 7 bytes.
They only
So they're
get
not
7
very good.
bytes, right?
They're not the cool ones that get 15, 23
So
bytes.
from the rest, as I said, I'm not sure what libc++ did in the recent past because the Constexpr thing made them change the implementation. I think Facebook's implementation, on the other hand, they could as well be compliant because they are mostly only looking at a byte. So I think the libc++ version is the one where I'm the least sure how compliant that is.
Okay, I'll go read Facebook's one then.
Perfect. Do that. Thank you.
Hi. I've been staring at this slide and something was bothering me and I just noticed what it was.
Perfect.
Is long m pointer not equal to m buff? That will have a bug in the unlikely but possible event that your pointer to the buffer happens to be the same size as the capacity that you allocated. You could end up getting an incorrect, a false positive.
If the pointer
if your pointer, sorry, if the pointer value happens to just be the same as your capacity for whatever reason that happened, unlikely.
Let's say pointer value would be 1, you're allocating 1 element, then the 2 would be 1, right?
Yeah.
Yeah, maybe you should file a bug report for Libstdc. I'm not sure what they are saying. But yeah, good catch. Thank you. All right. I see no more questions. Then have a lovely rest of your conference and see you around. Thank you.